Welcome to the Deep Dive, where we explore the fascinating forces that often operate behind the scenes in our world.
Hey there.
Today, we're plunging into, well, the heart of industry with a look at catalysis. Think of it as the unsung hero that makes countless everyday processes work faster and smarter.
Definitely. It's everywhere, even if you don't always see it.
And our roadmap for this journey is the comprehensive book, Industrial Catalysis, Optimizing Catalysts and Processes by Wijngaarden, Kronberg, and Westerterp. Quite a mouthful.
Oh, yeah, it is. But it's packed with crucial information. And for this deep dive, we're really aiming to extract the core ideas about industrial catalysis.
Okay.
Our goal is to give you a clear understanding of what it is, where it's happening all around us, and, the fundamental principles that make it so vital.
So kind of a shortcut to getting a solid grasp of this essential field.
Exactly. Consider this your guided tour.
Okay, so what are we actually going to unpack today? What's the plan?
Well, we'll start with the basic definition. What is catalysis? Then look at how these catalysts do their work inside industrial reactors.
Right, the practical side.
Yeah. We'll explore the different kinds of reactors that are used. And finally, we'll look at how we measure, just how well these catalytic processes are performing.
Sounds like a good plan. Ready to dive in?
Absolutely. Let's start with the basics. Catalysis, as our source lays out in section 1.1, is essentially speeding up a chemical reaction.
Okay.
By adding a small amount of the substance, the catalyst, which, and this is key, doesn't get used up in the process itself.
So it helps out but comes out unchanged at the end.
Pretty much. It's like finding a shortcut on a long and winding road, chemically speaking. What's really interesting is how this tiny addition can have such a massive impact on how fast a reaction goes.
Right, it's like a chemical choreographer maybe. Guiding the molecules to react in the right way, much faster than they would on their own.
That's a good analogy.
Now, the book mentions two main types, right? Homogeneous and heterogeneous catalysis. What's the key difference there?
Good question. In homogeneous catalysis, the catalyst is in the same phase, think liquid or gas, as the substances that are reacting.
Like dissolving something.
Yeah, imagine dissolving sugar in water. The sugar, or catalyst in this analogy, is dispersed throughout the water phase. However, in the industrial world, the book really emphasizes heterogeneous catalysis.
Okay.
Here, the catalyst is in a different phase. Usually it's a solid, while the reactants are typically fluids, gases, or liquids flowing over or through that solid surface.
And why is that one more common in industry?
Well, often it's because it's just much easier to separate the solid catalyst from the liquid or gaseous products at the end of the reaction. Makes the whole process cleaner, simpler to manage.
Okay, so picture a stream of gas flowing over a bed of solid pellets. That's our heterogeneous catalyst at work, making reactions happen right there on its surface. So section 1.2 dives into how this works inside an industrial reactor. What are the crucial things to understand about this setup? It's not just the catalyst, is it?
No, definitely not. What's fascinating here is how several physical processes come into play. Think about that fluid, whether it's a gas or a liquid, moving through a packed bed of these catalyst particles, often shaped like little pellets.
Right.
For the reaction to happen efficiently, it's not just about the catalyst's chemical properties, the way the fluid flows, how fast and how turbulent it is plays a big role.
How things mix.
Yeah, and crucially, the reactants need to be able to get from the bulk fluid to the surface of the catalyst that's mass transfer.
Okay.
And any heat that's generated or consumed by the reaction needs to be managed effectively. That's heat transfer. All these factors, they work together to determine the overall reaction rate.
And those catalyst pellets themselves aren't just solid chunks, are they? I remember reading they often have a hidden advantage in their structure.
Exactly. You're thinking about porosity. The book points out the significant benefit of using porous catalyst pellets.
Porous, meaning full of tiny holes.
Right. These pellets are riddled with tiny channels and pores inside. This internal network dramatically increases the total surface area available for the reaction to occur.
So it's not just the outside surface area.
Not at all. Think of it like a complex maze inside a small object. While the external size might not be that large, the total area within all those pores can be enormous, sometimes hundreds of square meters per gram.
Wow.
This increased surface area means there are many, many more active spots where the reactant molecules can come into contact with the catalyst and react, leading to much higher conversion rates.
That makes sense. More places for the action to happen. Now let's talk about the workhorses themselves, the catalytic reactors covered in section 1.3. The book distinguishes between reactors using larger chunks of catalyst and those using very fine particles. Let's start with the big stuff in section 1.3.1. What kind of setups are we talking about?
So thinking about industrial operations, reactors using large catalyst particles, often in what's called a fixed bed, are very common.
Fixed bed meaning the catalyst stays put.
Exactly. Imagine a big container like a tank or a tube filled with these catalyst particles, and the gas or liquid reactants simply flow through this stationary bed. The book mentions that these can operate with just a gas or just a liquid passing through.
Single phase?
Right, or even with both a gas and a liquid present simultaneously, which is multi-phase operation.
And I remember reading that managing the temperature in these larger systems is really important. Why is that again?
That's a critical point, especially for reactions that release a lot of heat, what we call exothermic reactions.
Okay.
If this heat isn't removed properly, it can lead to problems. It might cause unwanted side reactions to occur, reducing the selectivity, making stuff you don't want.
Right, less efficient.
Or it could even damage the catalyst itself, making it less effective over time. So temperature control is huge.
How do they control it?
Well, the book gives examples like adiabatic packed beds, where basically no heat is intentionally added or removed, so the temperature changes as it goes. Then there are cooled tubular reactors, which have cooling systems, maybe jackets or internal tubes, built right in to control the temperature.
I see.
It also mentions trickle bed reactors, often used for gas-liquid reactions over a solid catalyst. Here, the liquid kind of trickles down over the catalyst, while the gas flows either in the same direction that's co-current or the opposite direction, countercurrent. Figure 1.1 of the book gives a nice visual of these types.
All right, so those are the reactors with larger stationary catalyst pieces. What happens when we go to the other extreme and use really tiny catalyst particles, as discussed in section 1.3.2? How does that change the reactor design?
Yeah, so with small particles, which can be just a few micrometers in size, things are quite different. Instead of being fixed in place, these tiny particles are suspended within the reaction mixture.
So they're floating around.
Essentially, yes. The book highlights two main types here. First, fluidized bed reactors. Here, a gas is pumped upwards through a bed of these solid catalyst particles at a speed high enough to lift them and make them behave almost like a fluid.
Like boiling sand.
Kind of. It creates very good mixing and excellent heat transfer because everything's moving around so vigorously. The other type mentioned is the stirred tank reactor. Here, you typically have a liquid phase, and a mechanical stir keeps the fine catalyst particles suspended in it. Figure 1.2 shows these setups.
And where would you use these types?
The book notes they're particularly useful for gas-solid reactions like hydrogenations and oxidations, where you really need good contact between the gas and the solid catalyst surface. The mixing helps achieve that.
So the size and whether the catalyst particles are moving or stationary really dictate the design of the reactor. And that design is tailored for specific types of reactions and the phases involved. Makes sense. Now, once these reactors are up and running, how do we actually judge if they're performing well? Section 1.4 introduces the key characteristics of reactor performance. What are the main things we need to look at?
The book points to three key metrics, really. First is the reaction rate.
How fast it's going.
Pretty much.
Yeah.
It tells us how quickly the desired chemical transformation is happening. It's often expressed as the amount of product formed per unit of time, per unit of catalyst, either volume or weight of catalyst.
Okay.
And it's heavily influenced by the conditions inside the reactor, like temperature and pressure. Equation 1.2 in the book shows a general way to write this rate, and it includes those important stoichiometric coefficients.
Ah, the numbers from the balanced chemical equation.
Exactly. They tell us the exact ratios in which the reactants and products are involved.
Right, so it's a measure of how much starting material is turning into product relative to the catalyst amount in time. What's the second crucial measure?
The second vital characteristic is selectivity.
Selectivity, making the right stuff.
You got it. In most industrial processes, we're aiming to produce one specific product. Selectivity tells us how good we are at getting that desired product compared to any unwanted byproducts that might also form.
Okay.
Equations 1.6 and 1.7 define selectivity, basically, as the ratio of the desired product formed to the amount of the key reactant that has actually been consumed or converted. The book also makes a careful distinction between selectivity and yield, which is our next metric.
Ah, okay, so selectivity is about getting the right stuff, and yield, the third measure, is about how much of the right stuff we actually get compared to what's theoretically possible, right?
Exactly. Equation 1.8 defines yield as the amount of the desired product we actually obtain from the reactor compared to the maximum amount we could possibly produce based on the amount of the main reactant we started with.
So ideally, you want both to be high.
Absolutely. In industrial catalysis, the goal is generally to achieve both high selectivity, making mostly the product we want, and high yield, getting as much of that product as possible out of the process.
Okay, great. We've established the basics, what catalysis is, how it happens in reactors, the different reactor types, and how we measure their success. Now, let's delve into Chapter 2, kinetics. This is really the science behind how these reactions actually occur and how fast they go. Section 2.1 lays out some general concepts. What are the fundamental ideas here?
Right, kinetics. At its heart, chemical kinetics is all about the speed of reactions. The book explains that elementary reactions happen when molecules collide.
Bump into each other.
Yeah, but they need to collide with enough energy to actually transform into new substances. A key idea introduced here is activation energy, often written as EOLers.
The energy barrier.
Exactly. It's like an energy hurdle that the colliding molecules have to overcome for the reaction to proceed. Equation 2.1 and figure 2.1 in the book illustrate this energy barrier quite nicely.
And temperature plays a big role here.
Oh, definitely. We learned about how temperature affects the reaction rate constant, which is $dollars following the Arrhenius equation. Generally, higher temperatures mean faster reactions because more molecules will have enough energy to jump over that activation energy barrier.
Makes sense. More energetic collisions.
Precisely. The book also points out that pressure, especially for gases, can influence reaction rates. Equation 2.2 shows this. Sometimes it's discussed using a concept called fugacity, which is essentially an adjusted pressure that accounts for how real gases behave, especially when they're not acting like ideal gases.
Okay, so it's all about getting enough energy to overcome that initial hump, and temperature is like giving the molecules a bigger boost. Now, section 2.2 specifically focuses on heterogeneous catalytic reactions, where the catalyst is a solid. What are the key steps involved when our catalyst is in a different phase than our reactants?
Yeah, this is where it gets really interesting for industrial applications. A typical heterogeneous catalytic reaction involves a sequence of steps. First, the reactant molecules, which are in the gas or liquid phase, need to adsorb onto the surface of the solid catalyst.
Stick to the surface.
Kind of, yeah. Think of it like molecules landing and sticking, at least temporarily. Second, once they're adsorbed, these reactants undergo the actual chemical transformation right there on the catalyst surface.
The reaction itself.
Right. And third, the product molecules that have been formed must then desorb, meaning they detach from the surface and move back into the gas or liquid phase.
So stick, react, unstick.
That's a simple way to put it.
Yeah.
And the book emphasizes that the overall speed of the entire catalytic process is limited by the slowest of these individual steps. Whichever step is the bottleneck controls the overall rate. We're also introduced to the concept of active sites on the catalyst surface-specific locations where the adsorption and reaction actually happen, and the idea of surface coverage, which is basically the fraction of these active sites that are occupied by reactant molecules at any given moment.
And these steps, they aren't always simple or independent, are they? The book mentions the Langmuir-Hinshelwood kinetic model. What's the main idea behind that? How does it describe the rate?
Ah, yes, Langmuir-Hinshelwood. It's a common model, briefly covered with equations 2.9 and 2.09, and illustrated in figure 2.4. It provides a way to understand the kinetics of reactions that happen on the surface of a catalyst. The core assumption is that the reaction occurs between species that are already adsorbed onto adjacent sites on the catalyst surface.
Okay.
A key feature of this model is how the reaction rate changes with the partial pressure or concentration of the reactants.
Okay.
At low partial pressures of a reactant, let's say reactant A, the reaction rate is often proportional to that pressure. More A means faster reaction. But as the partial pressure of A increases, more and more of those active sites become occupied by A molecules. Eventually, at very high partial pressures, pretty much all the active sites are covered with A. At that point, the reaction rate becomes independent of the pressure of A. We call this zeroth order kinetics with respect to A. Adding more A doesn't help because there are no free sites left.
So it saturates, like a highway getting full.
Exactly. That's a good way to think about it. The catalyst surface gets saturated. The book gives some real-world examples where we see this kind of behavior, including the oxidation of carbon monoxide, CO, the hydrogenation of ethylene, C2H4,
Yeah.
and the decomposition of nitrous oxide, N2O.
So initially, more reactant leads to a faster reaction, but eventually the catalyst surface gets overwhelmed and adding more reactant doesn't really speed things up much anymore. That makes sense.
Right.
Now, section 2.3 shifts our attention to the performance of the catalyst itself, specifically looking at deactivation and selectivity again. We touched on selectivity earlier, but what exactly is deactivation and why is it such a big concern?
Catalyst deactivation is a huge challenge in industrial catalysis. Section 2.3.1 explains that over time, catalysts can lose their ability to speed up reactions. They become less active.
They'll wear out?
Sort of, yeah. Two common causes are mentioned. One is fouling, where deposits like coke, which is basically a carbon-rich gunk, build up on the catalyst surface and physically block the active sites. Reactants just can't get to them.
Like clogging pipes.
Exactly. The other is poisoning. This happens when certain compounds present in the feed stream, even in tiny amounts like maybe sulfur compounds, strongly absorb onto the active sites. They essentially stick there permanently, blocking them off and making them unavailable for the desired reaction.
So the catalyst gets clogged up or its working parts get jammed by impurities. And section 2.3.2 reminds us that even as catalysts lose activity, maintaining good selectivity, still making mostly the desired product, remains really important.
Absolutely. That's crucial. Even if a catalyst is gradually losing its overall oomph, its activity, we still want it to primarily facilitate the reaction we're interested in, not suddenly start making more junk.
Right.
The properties of the catalyst itself and the conditions under which the reaction is run, temperature, pressure, etc., can significantly influence both the initial selectivity and how that selectivity changes as the catalyst ages and potentially deactivates.
Okay. Finally, in this chapter, section 2.4 looks at kinetics in practice. It sounds like there's often a gap between the neat theoretical models we've been discussing and the messy reality of industrial processes. What are some of the challenges highlighted here?
Yeah, the book injects a necessary dose of realism here. It points out several difficulties in coming up with truly reliable kinetic rate expressions that perfectly predict what happens in a full-scale industrial reactor.
Like what?
Well, for example, even different batches of what is supposed to be the same catalyst can show surprising variations in their activity and selectivity. Manufacturing isn't always perfectly consistent.
Okay.
Also, the accuracy of the experimental measurements we take in the lab to determine these kinetic parameters can have limitations. Measuring things precisely at reaction conditions isn't always easy. Furthermore, the actual reaction conditions inside an industrial reactor, things like temperature and the concentrations of reactants, might not be perfectly uniform throughout the whole reactor bed. You can get hotspots or concentration gradients.
Right. Not perfectly mixed.
Exactly. Which can affect the observed kinetics. The idealized conditions we often assume in our theoretical models, like perfect mixing and constant temperature everywhere, just don't always hold true in the real world. Figures 2.7, 2.8, and 2.9, along with table 2.1 in the book, illustrate some of these complexities and the discrepancies that can pop up when we try to apply theoretical kinetics directly to real industrial data.
Okay, so kinetics gives us the fundamental rules of the game, but actually applying them in a real industrial setting requires careful consideration of all sorts of practical factors and potential deviations from those ideal conditions. That makes sense.
It's a constant challenge for chemical engineers.
Now, Chapter 3 shifts gears and takes us into the more tangible realm of production and physical characteristics of solid catalysts. Section 3.1 immediately emphasizes the importance of the physical structure of a catalyst. Why is this so critical for its performance? We touched on porous earlier.
Yes, and the book makes it clear right at the beginning of Chapter 3. The overall rate at which an industrial catalyst can convert reactants is paramount, right? And this rate is very strongly influenced by its physical characteristics. Most notably, the amount of surface area available for the reaction to happen.
The internal surface area in those pores.
Exactly. And also how efficiently reactants and heat can be transported to and from those surfaces within the catalyst particle. Section 3.1 defines the different sizes of pores that can exist. Macropores, which are the bigger ones, over 50 nanometers.
Like highways.
Sort of, yeah. Then mesopores, the medium ones, between 2 and 50 nanometers, and finally micropores, which are really tiny, smaller than 2 nanometers. The book also introduces equations on page 27 that show the relationship between the surface area per unit volume of the particle, sans Bakar, the average radius of the pores, and the porosity, epsilon. That's the fraction of the volume that's empty space. It highlights how these structural features are all interconnected.
And different pore sizes do different jobs.
Generally, yes.
Mm-hmm.
Larger pores might allow for easier access for bigger molecules into the pellet, while the smaller pores, the micro and mesopores, provide the vast majority of the actual surface area where the reaction occurs.
So it's not just about what the catalyst is made of chemically. The way it's physically put together at a microscopic level is just as important.
Absolutely critical.
Section 3.2 then delves into how these catalysts are actually manufactured. Catalyst manufacture. It sounds like a pretty involved process based on the list of steps.
It certainly is. Section 3.2.1 outlines the main ingredients you typically find in an industrial catalyst. There's the active catalyst agent itself, the material that actually does the chemical work.
The magic ingredient.
Yeah. Then there's the support or carrier material. This usually provides a high surface area to spread the active agent out on, and it also gives the catalyst particle mechanical strength and stability.
Like a scaffold.
Good analogy. And finally, there are often promoters, additional substances added in small amounts to enhance the catalyst performance in various ways. Maybe boost activity or improve stability or selectivity.
Okay, active agent, support, promoters. What are supports usually made of?
Common ones listed are things like alumina, silica gel, activated carbon, and zeolites. Each has its own set of properties like surface area and pore structure.
And the steps to make them.
The book lists general steps like precipitation, washing, drying, calcination, which is a high-temperature treatment, impregnation, which is depositing the active agent onto the support, leaching for some types, and thermal fusion forming.
That's a lot of steps. The book then goes into more detail on some specific methods, starting with precipitated catalysts in section 3.2.2. What's the core idea here?
Precipitation involves forming a solid catalyst precursor directly from a liquid solution. By carefully controlling the chemical conditions, like pH and temperature, manufacturers can influence important properties of the final catalyst, like its crystallinity, how ordered the structure is, and the size and distribution of its pores. The book gives an example reaction on page 30.
Okay, so you're basically making the solid material from scratch out of a solution. Next up is impregnated catalysts in section 3.2.3. This sounds like we're essentially loading the active component onto a pre-made porous material.
Exactly. Impregnation is a very common technique. You start with the porous support material, which acts kind of like a sponge. Then you soak it in a solution containing the active catalytic component.
So the active stuff gets drawn into the pores.
Right. Subsequent steps like drying and activation are then crucial to make sure that the active component is spread out as evenly as possible over the high surface area of the support. This uniform distribution is really key to maximizing how much of the active catalyst is actually accessible to the reactants.
Got it. Section 3.2.4 talks about skeletal catalysts. The name makes me think of a framework or something with lots of empty space. Is that the idea?
That's a great way to think about it. Skeletal catalysts are typically made starting from an alloy, a mixture of two or more metals. One metal is the active catalyst, and the other is usually less active and can be selectively dissolved away or leached out, often using a strong acid or base.
So you remove part of the original alloy.
Yes. This process leaves behind a highly porous, three-dimensional network, a skeleton of the active metal, which has a very high surface area. Rainy nickel is a classic example, used widely in hydrogenations.
Interesting. Then we have fused and molten catalysts in section 3.2.5. These sound like they're created under pretty extreme conditions, maybe high temperatures.
You're right. These types of catalysts are prepared by literally melting the different components together at very high temperatures. Once the mixture cools and solidifies, it forms a hard, often quite robust material that can withstand tough, high-temperature process conditions.
Any examples?
A prime example mentioned is the iron oxide catalyst, P3O44, used in the huge industrial process for making ammonia. This catalyst often includes other metal oxides, like potassium and aluminum oxides, which act as promoters to boost its performance and lifetime.
Okay. We then have calcination in section 3.2.6 and reduction in section 3.2.7. These sound like important finishing steps that happen after the basic catalyst structure is formed. What do they achieve?
They are indeed crucial activation or finishing steps. Calcination is a heat treatment process, usually done in an oxidizing atmosphere like air at high temperatures. Its purpose is to burn off any volatile stuff left over from earlier manufacturing stages, maybe organic residues from precipitation or impregnation. It also helps to stabilize the physical structure of the catalyst support.
Okay, so it cleans it up and strengthens it. What about reduction?
Reduction is often done after calcination, typically using a reducing gas like hydrogen. This step is often necessary to convert metal oxides, which might have formed during calcination or were part of the precursor, into their active metallic form. Many catalysts need the metal itself, not the oxide, to be catalytically active.
Ah, so it's activating the metallic component. Finally, in the manufacturing section, 3.2.8 discusses shape formation of the catalyst particles. It seems like the shape isn't just random. It must serve a purpose in the reactor. Why shape them?
Absolutely. The shape and size of the catalyst particles can have a significant impact on how the catalytic reactor performs overall. The book mentions common forms like pellets, which are often cylinders or spheres, extrudates, which are formed by pushing a paste through a die to create various shapes, like little noodles or stars.
Stars, really?
Yeah, sometimes complex shapes are used to optimize flow and surface area. Also granules, flakes, and fine powders. Table 3.2 gives an overview.
And why does the shape matter so much?
It can affect things like the pressure drop across a packed bed of catalysts, how much resistance the fluid feels as it flows through. Lower pressure drop is usually better. It also affects the overall surface area available for reaction within a given reactor volume and how easily reactants can get to the external surface. Methods like tableting, compressing powders into pellets, and extrusion are used to create these specific shapes.
So from choosing the materials all the way to the final shaping of the particles, making an effective industrial catalyst is a complex and carefully engineered process.
Definitely a lot goes into it.
Now, once we have these catalysts, how do we actually analyze their physical properties to understand what we've made? Section 3.3 talks about physical characterization. What are the key things we need to measure?
Right, characterizing the catalyst is crucial. Section 3.3 highlights several key physical properties. First is the void fraction, discussed in Section 3.3.1. That's basically the proportion of the total volume of catalyst bed that is empty space between the particles.
Why measure that?
It's important for figuring out how much fluid can flow through the bed and what the resulting pressure drop will be. Second, surface area, covered in Section 3.3.2. As we said, this is paramount because the reaction happens on the surface.
How do you measure the area inside all those tiny pores?
A common technique is called BT adsorption. It involves measuring how much gas, usually nitrogen, adsorbs onto the catalyst surface at very low temperatures and different pressures. From that data, you can calculate the total surface area.
Clever. What else?
Third is the pore size distribution, discussed in Section 3.3.3. This tells us not just the total pore volume, but the range and volume of pores of different sizes within the catalyst particle.
And why is the distribution important?
Because it affects how easily reactant molecules can diffuse into the interior of the catalyst, where the active sites are, and how quickly product molecules can diffuse back out. Different reactions might need different pore structures. Methods like mercury intrusion porosymmetry are used to figure out this distribution.
So we need to know not just the total surface area, but also the pathway to get there, the pore structure, and how the catalyst packing affects the flow. That leads us naturally to Section 3.4, mass and heat transfer in porous catalysts. We touched on how important this is earlier, but let's really dig into the details inside the pellet.
Absolutely. Section 3.4.1 really hammers home the point that while the intrinsic chemical reactivity of the catalyst material is fundamental in porous catalysts, the overall rate of the reaction we actually see can be significantly limited by transport phenomena.
Meaning how fast things move around inside.
Exactly. How quickly reactants can reach the active sites deep within the pores, and how effectively products and heat can be transported away. If these transport processes are slow compared to how fast the chemical reaction could happen, then the inner parts of the catalyst particle might not be used as efficiently as the outer parts. This reduces the overall effectiveness of the catalyst.
Okay. Section 3.4.2 then introduces ordinary diffusion in multi-component gases. This is basically how gases mix and move due to concentration differences, but we need to consider this happening within the tiny winding channels of the catalyst pores, right?
Yes, precisely. The book introduces Fick's law as a way to describe this process, along with the concept of diffusion coefficients, which quantify how easily a particular gas species moves through another gas or mixture. What's important to remember, though, is that these diffusion coefficients aren't just fixed numbers.
They depend on conditions.
Right. They depend on factors like the temperature, the total pressure, and the composition of the gas mixture, as shown in equations 3.13 through 3.16 and illustrated by tables 3.3, 3.6, 3.7, and 3.8. And in the very small spaces of catalyst pores, the way molecules move can become even more complicated than in open space because they bump into the pore walls frequently.
And that complexity leads us to Section 3.4.3, models of mass transport in porous media. It sounds like we need more sophisticated ways to describe what's going on inside those intricate pore networks than just simple Fick's law.
Indeed. The book introduces the dusty gas model in section 3.4.3.1 and figure 3.4. This is a more comprehensive model that tries to account for the movement of different gas molecules within the porous medium by considering both collisions between the gas molecules themselves and collisions between the gas molecules and the pore walls.
Okay, so it includes wall collisions.
Yes, and that's especially important when the pore sizes become very small, comparable to the mean free path, the average distance a gas molecule travels before hitting another molecule. When molecule wall collisions dominate, we call that Knudsen diffusion.
But is the dusty gas model used often in practice? It sounds complicated.
It is quite complex. So for more practical engineering calculations, a simplified approach is often used. The effective diffusivity concept, described in section 3.4.3.2 and equations 3.26 and 3.27.
Effective diffusivity, like an average or adjusted value.
Exactly. This concept uses a single effective diffusivity to represent the overall rate of diffusion of a particular species within the porous structure. This Betterle value bundles together the intrinsic diffusion coefficient of the molecule in free space with factors related to the catalyst structure. Its porosity, the fraction of volume that's pores, and its tortuosity, how winding and indirect the path through the pores actually is.
So it accounts for the maze-like structure.
Right. It's a lumped parameter that makes calculations more manageable. Finally, section 3.4.3.3 introduces the concept of material balance equations in steady state, equations 3.30 and 3.31. These equations help us understand how the concentration of a reactant or product changes as it moves through a small section of the catalyst pore. They balance the rate it diffuses in or out with the rate it's consumed or produced by the reaction happening right there, assuming the concentrations aren't changing over time.
So the effective diffusivity is a practical way to simplify a complex reality, allowing us to make calculations that account for the fact that diffusion in a porous material is slower and more complex than in open space.
Precisely. It's a very useful engineering approximation.
And section 3.4.5 then briefly touches on mass diffusivities in gases and liquids, giving us some general equations, 3.37 and 3.38, for estimating these fundamental transport properties needed for the other calculations.
Yes, these provide useful correlations for getting a ballpark estimate of how quickly molecules can diffuse in the gas or liquid phase itself, which are often needed as inputs for the more complex models of diffusion within the porous catalysts.
Okay, we've zoomed right in on what's happening inside the catalyst particle. Now, Chapter 4 broadens our perspective again to look at catalysis and external transfer processes. Section 4.1 reminds us that the journey for a reactant doesn't start inside the pore. It has to get to the outside of the catalyst particle first.
Exactly. That's a crucial step often overlooked. Section 4.1 highlights the role of mass transfer from the bulk fluid, the mainstream of reactants flowing through the reactor, to the external surface of the catalyst particle. Only then can it start diffusing into the pores.
And this step can also be a bottleneck.
It certainly can. If the reactants can't get from the fluid to the catalyst surface quickly enough, that external mass transfer step can limit the overall process rate, even if diffusion inside the pellet is fast and the catalyst is very active. The book introduces the concept of a mass transfer coefficient to quantify how effectively this external transport occurs.
And then Section 4.2 discusses how we can actually estimate these external transfer rates, heat, and mass transfer coefficients for flow around catalyst particles. It looks like things get even more complicated when we have different phases involved, like gas and liquid.
You're right.
Yeah.
Estimating these transfer coefficients is complex. It depends heavily on how the fluid is flowing around the catalyst particles, which is often characterized by dimensionless numbers like the Reynolds number. It also matters significantly whether we have just a single phase, like only gas or only liquid flowing, or a multi-phase system like a gas and a liquid flowing together over the solid catalyst, common in trickle beds, or even a three-phase system sometimes. The book provides some correlations like equation 4.9 for single-phase systems and more complex equations mentioned on page 68 for multi-phase scenarios to help estimate these rates based on fluid properties, velocity, particle size, and so on.
Right, lots of factors. Section 4.3 then brings up a potentially serious issue: thermal behavior of catalyst particles and pellet runaway. That sounds quite alarming. What's pellet runaway?
It can be alarming. For reactions that release heat, those exothermic ones we mentioned,
Yeah.
the temperature inside the catalyst pellet can become significantly higher than the temperature of the surrounding bulk fluid. This happens because the heat is generated inside the pellet where the reaction occurs, and it takes time for that heat to conduct out to the surface and then transfer to the fluid.
So the inside gets hotter than the outside.
Potentially, yes. This temperature difference can, in turn, further increase the local reaction rate inside the pellet, remember Arrhenius. In some cases, this can create a positive feedback loop leading to thermal instability or runaway, where the reaction rate increases uncontrollably.
What happens then?
It could damage the catalyst, cause unwanted side reactions, or even pose safety risks due to rapid temperature and pressure increases. The book introduces dimensionless numbers like the Prater number, which relates temperature rise to concentration drop, and the Thiele modulus, which we saw relates reaction rate to diffusion to help characterize these temperature and concentration gradients within the catalyst. Figures 4.4 through 4.7 in the book illustrate these phenomena and how temperature and concentration profiles might look inside a pellet under different conditions.
So managing heat isn't just about protecting the catalyst, it's also about maintaining control over the reaction itself and ensuring safety. That's critical.
Absolutely.
Finally, in this chapter, section 4.4 provides criteria for the absence of transport limitations. How do we know in practice when we need to be seriously concerned about these mass and heat transfer effects, potentially slowing down our overall reaction? When can we maybe ignore them?
This section gives us some practical guidelines and rules of thumb. It discusses criteria, with the Weiss-Prater criterion being a famous example, that can be used to estimate whether internal transport limitations, diffusion inside the pores, or external transport limitations, transfer from fluid to surface, are significantly affecting the overall observed reaction rate.
How do they work?
Basically, you calculate these criteria using experimental reaction rate data and the known properties of the catalyst, like particle size, diffusivity, and the reaction system, like kinetics, heat of reaction.
Yeah.
If the calculated value falls below a certain threshold, you can often reasonably assume that transport limitations are negligible for your purposes.
And if they are significant?
Then you know you need to consider them in your reactor model, and perhaps think about modifying the catalyst design, like using smaller particles or different pore structure, or the operating conditions, like increasing flow rate or improving heat removal, to minimize these limitations and get closer to achieving the true intrinsic reaction rate of the catalyst.
Okay, that's really useful for practical design. Now that we have a good grasp of the theory and the physical aspects, Chapter 5 moves into the practical realm, experimental methods. How do we actually measure all this stuff? Section 5.1 focuses on measuring the rate at which molecules diffuse within those porous solids. It lists several different techniques.
Exactly. Accurately determining how quickly different molecules move through the specific pore structure of your catalyst is crucial for developing reliable models and for designing efficient reactors. You can't always just rely on general correlations. Section 5.1 outlines several experimental methods used for this.
Like what?
The diffusion cell method, described in 5.1.1 and shown in Figure 5.1, often involves placing a catalyst pellet or membrane between two compartments containing different concentrations of a gas. You then measure the rate at which the gas diffuses through the pellet over time.
Okay.
Steady-state methods, covered in 5.1.2, equations 5.1, 5.3, involve setting up a constant flow of gas through the catalyst pellet and measuring the resulting concentration difference across it when things stabilize.
Right.
Unsteady-state methods, discussed in 5.1.3 and Figure 5.2, look at how the system responds over time to a sudden change in concentration or pressure on one side of the catalyst pellet. Analyzing that transient response gives you diffusion information.
And chromatography.
Yes, section 5.1.4 briefly mentions chromatographic techniques. Here, you might inject a pulse of a tracer gas into a carrier gas flowing through a packed bed of the catalyst. As the pulse travels through the bed, it broadens due to diffusion effects. Analyzing the shape of the exiting pulse can provide information about diffusion rates.
These all sound like quite clever, indirect ways to probe what's happening inside a solid material. Section 5.2 then shifts focus to the measurement of reaction rates. This seems absolutely fundamental to understanding how well our catalyst is doing its job.
It really is. Obtaining accurate data on the rate of a catalytic reaction under different conditions, temperature, pressure, concentrations, is essential for everything reactor design, process optimization, even for figuring out the fundamental mechanism of how the catalyst works. Section 5.2.2 discusses various types of laboratory reactors specifically designed for determining reaction kinetics.
What are the main types?
One common type is the integral reactor, described in 5.2.2 mini-equations 5.37 onward, Figure 5.3. These reactors are designed to achieve a significant conversion of reactants, maybe similar to what you'd see industrially. Because the concentration changes considerably as the reactants flow through the reactor, you need to mathematically integrate the rate equation along the reactor length to back out the kinetic parameters.
So it's more complex to analyze?
It can be. The differential reactor, on the other hand, discussed in 5.2.2.2, is designed to operate at very low conversions. The idea is that the concentration of reactants changes very little as they pass through the catalyst bed.
Why do that?
Because it allows you to directly measure the rate of reaction at what is essentially a single known concentration, making the data analysis much simpler. You get the rate directly without needing integration.
I see the trade-off. What else?
Section 5.2.3 introduces the single pellet diffusion reactor, figure 5.8 equation on page 101. This is specifically designed to study both diffusion and reaction simultaneously within just one catalyst pellet, allowing you to directly investigate the interplay between them. Section 5.2.4 briefly mentions dynamic methods, which involve studying how the reaction rate responds to intentional, time-varying changes in reaction conditions.
And other types.
Yes. Section 5.2.5 mentions other specialized reactors, like recycle reactors, where some of the product stream is mixed back with a feed to control concentration and temperature, and spinning basket reactors, figures 5.6 and 5.7, where the catalyst is held in a spinning basket to ensure good contact with the fluid. These are also used for specific types of kinetic studies, often trying to minimize external mass transfer limitations.
It sounds like there's often a trade-off in lab reactor design between achieving high industrially relevant conversion and being able to easily and accurately calculate the intrinsic reaction rate without complications from concentration changes or transport effects.
That's a very good summary of the challenge, yes.
Section 5.3 then covers some general aspects of kinetic investigations, highlighting important considerations for getting reliable results. What should we keep in mind?
This section really emphasizes that getting trustworthy kinetic data isn't just about picking the right reactor. It requires careful planning, meticulous execution of experiments, and rigorous analysis of the results. Section 5.3.1, for example, discusses criteria for ideal mixing in a recycle reactor. Equations 5.49 and 5.50, you need to ensure your assumptions about mixing are actually valid.
And errors.
Absolutely. Section 5.3.2 highlights potential sources of errors in the determination of kinetic parameters, using equations 5.69 and 5.71. It's a reminder that all experimental data have some degree of uncertainty, measurement errors, sampling issues, analysis inaccuracies, and it's crucial to be aware of these potential errors when interpreting kinetic results and developing rate equations based on them.
Good point. Okay, we've explored how we measure diffusion and reaction rates experimentally. Now, Chapter 6 introduces a really important concept for understanding how well porous catalysts are actually working in practice, the calculation of effectiveness factor. Section 6.1 mentions there's a lot of research literature on this topic. So what exactly is this effectiveness factor all about? Why is it so important?
As Section 6.1 points out, the effectiveness factor, usually represented by the Greek letter eta, is a really crucial parameter. It quantifies how much the actual rate of reaction occurring within a porous catalyst particle is reduced because of the limitations imposed by the diffusion of reactants getting into the pores.
So it's a measure of how well the inside of the catalyst is being used.
Exactly. It's defined as the ratio of the actual observed rate of reaction to the hypothetical rate that would occur if the entire internal surface of the catalyst were exposed to the same reactant concentration as the bulk fluid outside the particle.
Okay.
In simpler terms, it tells us how effectively we're using that vast internal surface area we talked about earlier. An effectiveness factor of 1 means there are no diffusion limitations.
Yeah.
Reactants get everywhere instantly, and the entire internal surface is working at its maximum potential for the given external conditions.
And less than 1.
A value less than 1 indicates that diffusion is slowing things down. Reactants are being consumed faster than they can diffuse into the pellet's core, so the concentration inside is lower than outside, and the overall reaction rate is lower than its potential. The inner part of the catalyst isn't pulling its full weight.
That makes perfect sense. If the reactant molecules can't easily reach the active sites deep inside the porous structure, then not all of the expensive catalyst material is being used effectively.
Precisely. Maximizing the effectiveness factor is often a key goal in catalyst design.
Section 6.2 then gives us some generalized definitions, including the zeroth Eris number and the first Eris number. What are these dimensionless numbers used for?
These Eris numbers are dimensionless groups, similar to the Reynolds number or Nusselt number in fluid dynamics and heat transfer. They help us characterize the relative importance of the reaction rate compared to the rate of diffusion within the catalyst pellet, specifically for different reaction orders. Section 6.2.1 defines the zeroth Eris number equation 6.23, which is relevant when the reaction rate is independent of the reactant concentration that's zeroth order kinetics.
Okay.
Section 6.2.2 formally defines the effectiveness factor again. Then section 6.2.3 introduces the first Aris number, and equation 6.24 and 6.25, which is specifically used for reactions where the rate is directly proportional to the reactant concentration first-order kinetics. Finally, section 6.2.4 briefly discusses the relationship between these two Aris numbers. They were related to another famous dimensionless group in this field.
The Thiele modulus.
Exactly, the Thiele modulus, often represented by failures. The Thiele modulus also compares reaction rate to diffusion rate, and the Aris numbers are essentially variations or generalizations of it for different kinetic situations.
Got it. And then section 6.3 provides a whole array of generalized approximations. There are equations from 6.54 to 6.62, a bunch of figures from 6.3 to 6.8, and then 6.1 to 6.18, and tables from 6.1 to 6.6, all for estimating this effectiveness factor. It looks quite involved. It seems like people have spent a lot of time on this.
Oh, absolutely. This is a classic topic in chemical reaction engineering, studied for decades. This section of the book presents various simplified equations and graphical correlations that have been developed over the years to estimate the effectiveness factor under different conditions without having to solve the underlying differential equations every time.
So these are practical tools.
Yes, very much so. These approximations take into account factors like the order of the reaction, zeroth, first, second, etc., and the geometry of the catalyst particle, whether it's a flat slab, a long cylinder, or a sphere. The Thiele modulus, or the relevant Aris number, usually appears prominently in these correlations.
So engineers can use these charts and equations, right? They provide practical tools for engineers to quickly estimate the effectiveness factor for a wide range of common scenarios, helping them to assess the impact of diffusion limitations and make informed decisions about catalyst and reactor design.
So these are essentially handy shortcuts and rules of thumb based on lots of mathematical work that help us quickly gauge how much the internal pore structure of our catalyst is hindering the overall reaction rate under different conditions.
That's a good way to put it.
Yeah.
They capture the essence of the complex interaction between reaction and diffusion.
Now, Chapter 7 moves into the realm of complex situations. It sounds like the somewhat idealized scenarios we've been discussing so far, maybe isothermal, single reaction, simple shapes, don't always capture the full picture in real-world catalytic processes.
That's very true. Industrial reality is often much more complex.
Section 7.1 focuses on intraparticle temperature gradients. We touched on the possibility of temperature differences within a catalyst particle earlier with the idea of pellet runaway. How do these temperature variations actually affect the effectiveness factor calculations we just discussed?
Right. As we discussed, exothermic or endothermic reactions can lead to significant temperature differences between the inside and the outside of a catalyst pellet. This obviously affects the local reaction rate constant, remember, Arrhenius, which in turn affects the concentration profile and the overall effectiveness factor. Section 7.1.1 introduces more sophisticated 2- and 3-parameter models, equations 7.1, 7.2, that go beyond the simple isothermal assumption and try to account for these simultaneous temperature and concentration variations within the particle.
So the math gets harder.
Significantly, yes. Section 7.1.2 then discusses adaptations of the Aris numbers using equations 7.9 through 7.13 plus figures and tables to incorporate these non-isothermal effects. Calculating the effectiveness factor becomes much more complex when temperature isn't uniform.
But can we sometimes ignore these temperature effects?
Fortunately, yes. Section 7.1.3 provides important negligibility criteria. These help us determine under what conditions we can actually get away with ignoring these temperature gradients within the catalyst and just use the simpler isothermal models. These criteria often depend on factors like the heat of reaction, the thermal conductivity of the catalyst, and the particle size.
That's really useful. Knowing when we can simplify our models is just as important as having the complex ones available.
Absolutely essential for practical engineering.
Section 7.2 then looks at bimolecular reactions, reactions that involve two different molecules reacting together on the catalyst surface. What new complexities arise here compared to reactions with just one reactant when we think about effectiveness factors?
When you have two different reactant species, say A and B, reacting together, the situation gets more complicated. You now have two concentration profiles developing within the catalyst pellet, one for A and one for B.
And they affect each other.
Yes, because the local rate of reaction depends on the concentrations of both A and B at that point inside the pellet. Section 7.2, with equations 7.29, 7.30, 7.36, 7.38, figure 7.5 discusses how the effectiveness factor for these bimolecular reactions depends not only on the individual diffusion rates of A and B and the intrinsic kinetics, but also on the relative concentrations of A and B in the bulk fluid and how they might compete for active sites or diffuse at different rates within the pores.
So one reactant might run out faster inside the pellet than the other?
Exactly. That can happen, leading to non-uniform reaction conditions and potentially affecting both the overall rate and the selectivity, especially if there are competing side reactions.
Okay, another layer of complexity. Section 7.3 then briefly brings up intraparticle pressure gradients. This is probably more of a concern for reactions that involve gases, right? Especially if the number of gas molecules changes.
Yes, pressure gradients within the porous structure of a catalyst are generally more significant for gas phase reactions. This is particularly true when there's a substantial net change in the number of moles of gas as the reaction proceeds. Say this is A and N of 2B or 2AB, or at very high overall reaction rates where there's a large flow of gas being consumed or produced within the catalyst pellet.
How does pressure gradient affect things?
Section 7.3, using equations 7.71, 7.73, figure 7.6, introduces the concept. These pressure differences within the pores can actually affect the effective diffusion coefficient of the gases, described by equations 7.74, 7.78, because diffusion rates can depend on total pressure. They can also influence the Eris numbers, equation 7.81, 7.86, figure 7.7. In most cases, the effect is small, but in extreme situations, a significant pressure drop across the catalyst pellet could potentially impact the overall reaction rate.
Okay. We then revisit bimolecular reactions in section 7.4, presumably layering on these other complexities like temperature and pressure gradients, with equation 7.104, 7.112.
Yes, it delves deeper into calculating effectiveness factors when multiple complexities occur simultaneously.
And then section 7.5 briefly touches on anisotropic catalysts that have different properties depending on the direction you're looking at within the pellet, like wood grain.
That's a good analogy. Anisotropy can arise from the manufacturing process. Maybe extrusion aligns pores in one direction. Section 7.5, with equation 7.126-7.130, mentions that in such cases, the diffusion characteristics and therefore the effectiveness factor can be different depending on whether diffusion is happening along the main pore direction or perpendicular to it. Adds yet another layer of complexity to the modeling.
Wow. Finally, section 7.6 provides a summary of complex situations with table 7.7 and equation 7.131. This sounds like a really helpful consolidation of all these non-ideal effects.
Exactly. After wading through all those complexities, this summary table serves as a very convenient reference. It lists the key characteristic dimensionless numbers like Thiel modulus, Prater number, different Eris numbers, and the criteria that can be used to quickly assess when these various complex situations, non-isothermal behavior, bimolecular reactions, pressure gradients, anisotropy, might be significant enough that you really need to take them into account in your analysis and reactor design.
A practical guide through the complexities. Okay, we've navigated through some pretty complex scenarios involving reaction, diffusion, heat transfer, and more. Now, Chapter 8 brings us back to a more design-oriented perspective, focusing on the design of catalyst pellets. It really brings home the idea that we can actually engineer these catalysts from the ground up for better performance, using all the principles we've discussed.
Precisely. This chapter ties a lot of it together from a practical design standpoint.
Section 8.1 discusses how the porous structure and observed reaction rate are intrinsically linked, as shown in figure 8.1. It feels like a recap, but with a design focus.
Yes, it revisits that critical relationship. It emphasizes again that the internal network of pores within a catalyst particle directly impacts the overall reaction rate that we actually observe in the reactor. As we've discussed, diffusion limitations within those pores lead to an effectiveness factor less than 1, meaning a lower overall rate than the catalyst material is capable of intrinsically. Figure 8.1 visually shows how the observed rate depends on the Thiel modulus, which itself depends on pore size, reaction rate constant, and particle size. It hammers home that just having a superactive catalyst material isn't enough.
But you need to structure it right.
Exactly. It needs to be presented in a physical form that allows reactants to easily access those active sites.
Section 8.2 then delves into the concept of optimal particle shape and size, illustrated in figure 8.2. It seems like the physical dimensions of the catalyst are not just arbitrary choices, but can be strategically designed to improve performance.
That's absolutely correct. Optimizing the shape and size of the catalyst pellet is a crucial strategy for minimizing the impact of diffusion limitations and maximizing that effectiveness factor, eta.
How does size help?
Well, generally smaller catalyst particles mean shorter internal diffusion paths. Reactants don't have as far to travel to reach the center. This reduces the resistance to mass transfer within the pellet and allows for a more uniform concentration of reactants throughout, pushing GETA closer to 1 car.
But smaller particles might cause higher pressure drop in a fixed bed.
Exactly. There's always a trade-off. You have to balance the improved effectiveness factor of smaller particles against the increased pressure drop they might cause. Shape also matters. Spheres, cylinders, rings, extradates all have different packing characteristics and surface area to volume ratios. The book also briefly introduces the interesting concept of bidisperse catalysts here.
Bidisperse. 2 types of pores.
Yes. Catalysts designed with 2 distinct size ranges of pores. You might have larger transport pores, macropores, that act like highways, allowing reactants to penetrate deep into the particle quickly. Branching off these highways are much smaller pores, micro or mesopores, where the bulk of the high surface area and active sites reside.
So easy access plus high surface area.
That's the idea. Designing a catalyst with this kind of hierarchical pore structure can be a very effective way to get the best of both worlds, minimizing diffusion limitations while maximizing the available active surface.
Clever design. Section 8.3 then takes a closer look at diffusion limitations again, but focusing on design solutions. Section 8.3.1 specifically discusses the distribution of catalytic material in pellets. This is a really interesting idea where you put the active catalyst within the support pellet can actually make a difference, not just uniform distribution.
Indeed. For certain types of reactions, it might actually be advantageous not to have the active catalytic material spread uniformly throughout the support pellet.
Why not?
We'll consider a very fast reaction. If the reaction happens almost instantly as soon as the reactant hits the active site, maybe there's no point having active sites deep inside the pellet where the reactant concentration will be very low anyway due to diffusion limits. In such cases, it might be better to concentrate the active material in a thin layer near the external surface of the pellet, an eggshell catalyst.
So you only put the expensive active stuff where it's going to be used?
Exactly. This minimizes the diffusion path length and makes better use of the active component. Section 8.3.1 uses the example of the dehydrogenation of butene to illustrate how different distributions of the active catalyst within the pellet, uniform versus eggshell, can affect not only the overall conversion rate but also the selectivity towards the desired product, especially if side reactions are sensitive to concentration.
Fascinating. And Section 8.3.2 provides a great real-world example, a poison-resistant catalyst for automotive emission control. How does the design of the catalyst pellet, in this case, help to address the problem of deactivation by poisons that we talked about earlier?
This is a fantastic practical illustration of clever catalyst design tackling a real-world challenge. In automotive catalytic converters, the catalysts face harsh conditions and are susceptible to poisoning by things like lead, less common now, thankfully, and phosphorus or sulfur compounds from fuel and oil additives.
Right.
The design of these catalysts often incorporates features to combat poisoning. One strategy is to create a layered structure or a specific distribution of the active catalytic components, like platinum, palladium, rhodium, within the pellet or washcoat structure. The idea might be to have a protective outer layer that traps some poisons, or to place the most sensitive components deeper inside, making it harder for the poison molecules to reach and deactivate all of the active sites quickly.
So you're designing it to sacrifice outer layers or make the poison trouble further?
Kind of, yes.
Yeah.
By strategically placing the active material and potentially incorporating poison traps, the catalyst can maintain its activity for a much longer period, meeting stringent emission standards over the lifetime of the vehicle, even in the presence of small amounts of these deactivating agents.
So it's really not just about creating a catalyst that is inherently active for a particular reaction. It's also about designing it in a very specific way, considering its physical pore structure, its overall shape and size, and even how the active material is distributed within it to optimize its performance and longevity in the face of real-world limitations like diffusion and deactivation.
Exactly. The physical design of the catalyst pellet itself is a truly crucial and often somewhat hidden aspect of the overall catalytic process performance. It's a key area where chemical engineering principles, transport phenomena, reaction kinetics, materials science all come together to create more efficient and durable catalysts for countless industrial applications.
Well, we have certainly taken an incredibly deep dive into the fascinating and clearly complex world of industrial catalysis, and it's all thanks to the comprehensive insights provided by Industrial Catalysis, Optimizing Catalysts and Processes by Wijngaarden, Kronberg, and Westerterp.
It's a dense book, but hopefully we've pulled out the key threads.
I think so. We've journeyed from the fundamental definitions right through to the complexities of reactor design, the details of catalyst manufacturing, the real intricacies of kinetics and transport phenomena both inside and outside the catalyst particles, and that vital concept of the effectiveness factor.
And as we've explored throughout this, the seemingly straightforward act of using a catalyst to accelerate a chemical reaction actually involves this remarkable and intricate interplay of chemistry, physics, and engineering. It's not simple at all when you look closely.
Definitely not.
The successful design and optimization of these industrial catalytic processes really demand a thorough, quantitative understanding of reaction kinetics, the fundamental principles of mass and heat transfer, and, as we just discussed, the detailed physical characteristics of the catalyst material itself.
So what's the big picture here for you, our listener? Hopefully you now have a much deeper appreciation for the often unseen engineering that underpins so many of the products and processes that we encounter in our daily lives.
Yeah, things like the fuels that power our cars and planes, the fertilizers that help grow our food, the vast array of plastics and polymers that shape our modern world. So many rely heavily on industrial catalysis.
And as we've only just touched the surface of this vast field today, remember that there are countless specific catalytic processes out there, each with its own unique chemistry, its own set of challenges, and often its own really innovative catalyst and reactor design solutions.
It's a field that's constantly evolving.
On that thought, maybe the next time you encounter a product or a process that you know relies on catalysis, take a moment to appreciate the sophisticated science and engineering that went into optimizing that seemingly simple chemical transformation. Perhaps this deep dive has even sparked your curiosity to investigate a particular catalytic process that's relevant to your own interests or field.
There's always more to learn.
Until our next exploration, keep those deep dives coming.